Welcome back. Problem 9-13. This problem is taken from chapter number 9, that is stress transformation, and book name is Mechanics of Material by R.C. Hibbeler. So statement is determine the equivalent state of stress on the element if it is oriented 30-degree clockwise from the element shown. Use the stress transformation equation. So you can see this is the state of stress where there is a shear force of 950 pounds and there is a compressive stress of 300 pounds, and this is its x-axis and y-axis. So you have been asked that when it is rotated 30-degree clockwise, so you have to find the state of stress on that element. So we'll find this. Let's start with the solution. So first we have been given that this is x-axis, clear, and this is your y-axis. So you can see along x-axis we do not have any stress, so sigma x is equal to 0, and sigma y, that is compressive, this is minus 300 psi. Also shear stress, which is tau of xy, is 950 psi. So I will write 950 and it is plus 950 psi. So using stress transformation equation, what we will do is that I will write using stress transformation equation. So first equation is that if you rotate it at any angle theta, so stress transformation for x component will be equal to sigma x plus sigma y divided by 2 plus sigma x minus sigma y divided by 2 cos of 2 theta plus tau of xy sine of 2 theta. So kindly memorize this formula. Now we have sigma x value, we have sigma y, we have tau of xy, and theta is given as 30-degree clockwise. So clockwise is taken as negative, so theta is minus 30 degree. So 2 theta will be equal to minus 60 degree. So put it in this formula. So when you rotate element 30-degree clockwise, so sigma x dash will be equal to 0 minus 300 divided by 2 plus 0 minus, and sigma x is minus 300 divided by 2 into cos of 2 theta is minus 60. So minus 60 degree plus tau of xy, which is 950 into sine of minus 60 degree. So when you solve this, you will get sigma x dash come out to be minus 898 psi. So this is the transform component in x dash direction. Clear? What is x dash? So x dash will be your this one. When you rotate it 30 degrees, so this will be your x dash and this will be your y dash. Clear? Now sigma y dash will be equal to, we have formula sigma y dash is equal to sigma x plus sigma y divided by 2 minus sigma x minus sigma y divided by 2 into cos of 2 theta minus tau of xy sine of 2 theta. So put the value, you will get sigma y dash is equal to 0 plus minus sigma y is 300 divided by 2 minus, and you will have 0 minus 300 divided by 2 into cos of minus 60 degree and minus 950, which is tau of xy into sine of minus 60 degree. So again, when you solve this, you will get sigma x dash and sigma y dash. So sigma y dash comes out to be 598 psi. Now we'll find tau of x dash and y dash. So for tau of x dash, y dash, we know that tau of x dash, y dash is equal to minus sigma x minus sigma y divided by 2 into sine of 2 theta plus tau of xy cos of 2 theta. So put the value minus 0 minus uh, sigma y is minus 300. So minus 300 clear divided by 2 into sine of minus 60 degree plus tau of xy is 950 into cos of minus 60 degree. That will be equal to tau of x dash y dash. Okay. Now when you calculate it, you will get tau of x dash y dash comes out to be 605 psi. So you have this sigma x, which is minus, sigma y is positive, and tau of x dash y dash is also positive. So if you want to represent on the element when it is rotated 30 degree clockwise, so it will be like this. Let this was the element. Clear? Okay. So you can see sigma x dash is minus 898. So sigma x dash will be compressive one. It will be perpendicular. Clear? This is your sigma x dash, and sigma y is 598. It is positive, so sigma y will be like this. In the direction of y dash, it will be sigma y, and your tau of x dash y dash will be also positive, so it will be like this. Clear? It will be like this. So you can put the place the value sigma y dash is 598 psi, sigma x dash was minus 898, and tau of x dash y dash will be equal to plus 605 psi. So this is the equivalent state of stress when this is rotated. This element is rotated 30 degree in clockwise direction. And that was all about this problem 9-13. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 9-15. This problem is taken from chapter number 9, that is stress transformation, and book name is Mechanics of Material by R.C. Hibbeler. So statement is the state of stress at a point is shown on the element. Determine the principal stress, and in B part the maximum in plane shear stress and average normal stress at that point. Specify the orientation in each case. So you can see this is state of stress. Sigma x is given as 45 megapascal. Sigma y, which is compressive, that is minus 60 megapascal, and this tau of xy is 30 megapascal. So all the datas are mentioned. So you have to find the principal stresses, which is sigma 1 and sigma 2. Principal stresses are the maximum stresses and maximum in plane shear stress and average normal stress in that case. And you have to specify the orientation of each element. So let's start with the solution. So as we know that we have been given sigma x, which is equal to 45 megapascal, sigma y is equal to minus 60 megapascal, and tau of xy is equal to 30 megapascal. So we know that principal stresses, which is equal to sigma 1 comma 2 is equal to sigma average, or we can say sigma x plus sigma y divided by 2 plus minus sigma x minus sigma y divided by 2 whole square plus tau of xy whole square. Now you have each value, you can find it. sigma 1 comma 2 is equal to 45 plus minus 60 divided by 2 plus minus sigma x is 45 minus minus 60 divided by 2 whole square plus tau of xy is 30. So 30 square. So when you calculate it, if you take this value 45 minus 60 divided by 2 plus 45 minus minus 60 divided by 2 whole square plus 30 square under the root. So this will give you sigma 1 will be equal to 53 megapascal. Clear? And if you subtract it, so you will get sigma 2 which is equal to 45 minus 60 divided by 2 minus 45 minus minus 60 whole square divided by 2 plus 30 square, and you will get sigma 2 will be equal to minus 68 megapascal. So these are the principal stresses that we covered in part number 1. Now we have to specify the orientation of each element in each case. So we will find the principal plane, orientation of principal plane where which this principal stresses acts. So orientation of principal stresses, and this orientation r theta can be obtained by using formula tangent of 2 theta p is equal to tau of xy divided by sigma x minus sigma y divided by 2. Clear? Now you have to put the value tau of xy is 30 divided by sigma x is 45 minus sigma y is minus 60 divided by 2. So you will get 0.5714. So tangent of 2 theta p will be equal to tangent inverse 0.5714, and you will get the angle 2 theta will be equal to 2 theta p will be equal to 14 point. So this angle is 29.74. So theta p1 is theta p will be equal to 14.87 degree. Now we have this theta p1. So using stress transformation equation, we will verify that where this theta 1 and sigma 1 and sigma 2 acts. So we know that stress transformation equation is sigma x dash is equal to sigma x plus sigma y divided by 2 plus sigma x minus sigma y divided by 2 into cos of 2 theta plus tau of xy sine of 2 theta. So we have 2 theta p is 29.74. We have sigma x and sigma y. So when you put the value, so you will get sigma x is 45 minus plus sigma y is minus 60 divided by 2 plus 45 minus minus 60 divided by 2 into cos of 29.74 degree, and this positive means that this will be counterclockwise, plus tau of xy, and tau of xy is 30 into sine of 29.74 degree. So when you calculate, you will get sigma x dash will be equal to 53 megapascal. So it means that you can see this is sigma x and sigma 1 is 53. So it means that let this is your x axis, clear, and this is your y-axis. And when you rotate this to angle 14, this is your theta p, which is equal to 14.87 degree. So your new x dash will be this one and your y dash will be this one. Clear? Sigma y dash, y dash, not sigma y dash. So correct it. Sigma, y dash. So if you draw the element like this, clear, state of element like this, so it means that your sigma x dash will be this one, which is positive. This will be your sigma x dash. Clear? Sigma x dash. And sigma x dash, or you can say this is the principal stresses, that is sigma 1, and sigma y, which comes out to be minus 68, so it will be compressive one. So this will be like this. This will be sigma 2, which is minus, as this is compressive, so I will write just 68 megapascal, and sigma 1 is equal to 53 megapascal. So this is state of stress for principal stresses. So you can see that this total angle is 90. So this will be, if you take this as another angle for, so this will be theta P2 and this will become to theta P1. So theta P2 will be equal to 90 minus theta P1, and that will be equal to 90 minus 14.87, which is equal to 75.13 degree. So in clockwise direction, so theta P2 will be equal to minus 75.13 degree, and theta P1 is which we have calculated 14.87. The positive sign means that it is in counterclockwise direction. Now we will move toward our second part and we will find the maximum in plane shear stress. So I will write it on next page. So in second part we have to find maximum in plane shear stress. So we know that maximum in plane shear stress is equal to maximum in plane shear stress is equal to sigma x minus sigma y divided by 2 whole square plus tau of xy whole square. So put the value, you will get sigma x was 45 minus sigma y is minus 60 divided by 2 whole square, and tau of xy was 30, so 30 square. And when you calculate it, you will get maximum in plane shear stress. You have to memorize this formula. So that will be equal to 60.5 megapascal. Also, we have been asked to find the average shear stress. So average shear stress is equal to sigma x plus sigma y divided by 2. That is 45 minus plus minus 60 divided by 2, and that come out to be minus 7.50 megapascal. Okay, now we have to determine the state of stress. For that we have to find the orientation of maximum in plane shear stress. So we can find it by using formula tangent of 2 theta s is equal to minus sigma x minus sigma y divided by 2 and divide by tau of xy. So put the value minus 45 minus 60 whole divide by 2, divided by top xy is 30. So when you calculate it, you will get 2 theta s will be equal to tangent inverse 1.75, or you can say that this theta s will be equal to 60.2 degree, minus 60.2 degree. Okay, so theta will be equal to, theta s will be equal to 30.1 degree. Clear? Now we will specify its state of stress. So let's say it was your initial x. Clear? And you have found that maximum or plane of principal stress was 14.9. Let me check it. Theta P1 14.87, which is 14.9. So 14.9 degree, and your element which was acting, the face was perpendicular to this. Clear? It will be like that, and this was your other face, and you can see you have theta s is 30 degree. So theta, this is theta s1, which is 30.1 degree. So theta s2 will be equal to um, uh, theta s2 will be equal to 90 degree minus 30.1 degree. Clear? And this angle was 90, sorry, this is minus 30, minus 60.9. Okay, so you will get uh, this theta will be equal to 59.9 degree. This is theta s2. I will explain it in a while. So when you cut, this is positive value, so it will be counterclockwise. So it means that when you cut this element or angle of 59.9 degree. Clear? So your shear stress will be like this. You can see this is 60.5. Clear? So your shear stress will be like this. This is maximum in plane shear stress. 60.5 megapascal, and the normal stress that will act perpendicular to this surface. This is average, and you can calculate it. It will make an angle of 30.1 degree. Clear? That will be in clockwise direction. Clear? And this angle is counterclockwise direction to cut, which will show that over that phase we have maximum in plane shear stress is 60.5 megapascal. So that was all about this problem 9-15, in which we have calculated principal stress sigma 1 and sigma 2, and we have represented its orientation on the element. And then in second part we have calculated maximum in plane shear and average stress and has specified on the element. I hope you have enjoyed this video. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 9-16. This problem is taken from chapter number 9, that is stress transformation, and book name is Mechanics of Material by R.C. Hibbeler. So statement is determine the equivalent state of stress on element at the point which represent the principal stresses, maximum in plane shear stress and associated average normal stress. Also for each case determine the corresponding orientation of the element with respect to the element shown and sketch the result on the element. So you can see this is the given state of stress where sigma x is 50 megapascal. There is no sigma y in y direction, no stress in y direction, and this shear stress is 15 megapascal. That will be negative. So we have to determine the principal stresses, maximum in plane shear stress, and average stress, and then we will have to specify the orientation. So let's start with the solution. So you can see this is your x, this is your y. So this face, which is usually x plane, clear. So tau of x in y, x is plane and y is the direction. So you can see on this plane the y is downward, so tau of xy is negative. Okay, so we know that principal stresses is equal to sigma 1 comma 2, and that is equal to sigma x plus sigma y divided by 2 plus minus sigma x minus sigma y divided by 2 whole square plus tau of xy whole square. Okay, now you have sigma x, sigma y and tau of xy, so you can just put the value. Sigma 1 comma 2 will be equal to 50 plus 0 divided by 2 plus minus 50 minus 0 divided by 2 whole square plus tau of xy, which is minus 15 whole square. So you will get, once when you take first it positive, so it will be sigma 1, and sigma 2 will be 50 plus 0 divided by 2 minus 2 will give, and with this term it will give you sigma 2. So when you solve this, you will get sigma 1 will be equal to 54.2 megapascal, clear. And when you take it negative in between these two terms, so sigma 2 will be equal to minus 4.15 megapascal. So this sigma 1 and sigma 2 are principal stresses, which are the maximum stresses acting on the element. Now we will specify its location or orientation. Specify orientation of sigma 1 and sigma 2. So we know that tangent, for that we will find theta p1. So we know that tangent of 2 theta p1 or 2 theta p is equal to tau of xy divided by sigma x minus sigma y divided by 2. So put the value minus 15 divided by sigma x is 50 minus 0 divided by 2. So from here you will get 2 theta p is equal to tangent inverse minus 0.6, and you will get 2 theta p will be equal to minus 30.96, and theta p1 will be equal to minus 15.48 degree. So this is the location of our orientation. When this element is rotated, it will at this rotation we will get the principal stresses. Now we know that this was your initial x-axis and this was your y-axis, clear. And when you rotate it minus 15.8, so your x dash, this is theta p, and that is minus 15.48 degree. So your y-axis, new y dash will be this one. This will be your y dash. And if you specify the element, it will be like this, clear. So we do not know or which phase, on what will be the stress at this phase, clear. Either it is sigma 1 or sigma 2. So for confirmation we will use stress transformation equation, and we will put the value of theta. We know that stress transformation equation is equal to sigma x dash, which is equal to sigma x plus sigma y divided by 2 plus sigma x minus sigma y divided by 2 into sine of 2 theta plus tau of xy sine of 2 theta. So put the value, we will get this sigma x dash is equal to 50 plus 0 divided by 2 plus 50 minus 0 divided by 2 into sine of minus 30.962 theta is this, plus tau of xy. So tau of minus 15 into sine of minus 30.96 degree. So when you calculate it, you will get sigma x dash comes out to be 54.2 megapascal. Now it means that this sigma 1 is acting on this face. So your sigma 1 is acting on this face, which is positive value. Clear? And your sigma 2 is on this, and since this value is negative, so it will be compressive. Clear? This is sigma 2, which is 4.15 megapascal, and this arrow shows that this is compressive. Now you can see that this angle is actually theta p2, and this angle is, let's say this angle is theta p2, and this is theta p1. So theta p2 is equal to 90 minus theta p2 is equal to 90 minus theta p1. Clear? So you can see that this theta p1, which is clockwise, so I will write theta p2 is equal to 90 minus 15.48, that will give you 74.52 degree counterclockwise. So it means that if you rotate it in counterclockwise, you can also say that this is theta p2. So this will give you the same principal stresses. Now we will move toward second part, which is maximum in plane shear stress. So in second part, we have to find the maximum in plane shear stress and average shear stress. So we know that maximum in plane shear stress is equal to sigma x minus sigma y divided by 2 whole square plus tau of xy whole square under the root. So put the value, sigma x was 50 minus sigma y is 0 divided by 2 whole square plus tau of xy, and tau of xy is minus 15 whole square, and we will take the under root. So when you calculate it will be 29.2 megapascal. And associated average shear stress is equal to sigma x plus sigma y divided by 2, and that is 50 plus 0 divided by 2 is equal to 25 megapascal. Finding this, we will find the orientation of maximum in plane shear stress. So we have formula that this tangent of 2 theta s is equal to minus sigma x minus sigma y divided by 2 divided by tau of xy. So put the value minus 50 minus 0 divided by 2 divided by tau of xy is minus 15. So it will be 1.667. So when you calculate 2 theta s, and you will have value, and if you divide it by 2, so you will get theta s will be equal to 29.5 degree. This will be theta s1, or you can say theta s2 is equal to 90 plus theta s1. So 90 plus 29.5 will be equal to 120 degree. So this will be equal to theta s2. Now you have theta s1 and s2, so you can just specify the orientation of this maximum in plane shear stress and average normal stress. So this was initial x, this is your y. Clear? So your new axis theta s is 29.5, so you can move toward 29.5, that is positive, so it means counterclockwise. So theta s1 is 29.5 degree and your y-axis will be, y dash will be this one. Clear? And if you draw the element, so let me draw it. If you draw this element like this, clear? So you can see that you will have a normal stress that will be acting over this. Let me choose a green color. It will be like this. This average stress is 25 megapascal, so it will be like this average. Clear? All these are average normal stress, which is 25 megapascal. Clear? And your shear stress will be maximum in shear stress is 29.5, so it will be like this. This will be your maximum in plane shear stress, which is 29.2 megapascal. Okay, so this is the orientation of this element. Now if we combine, represent this case and this case and draw the state of stress, so you can see that you have, this is your initial x axis, and this theta is given as this theta, which is given as 15.5. Clear? 15.5 in clockwise. So if you move clockwise like this is your x dash and this is your clockwise 15.5 or 15.48, which is 15.5 degree. Clear? And here you draw the element, the face of the element. Clear? And this is the other face. Clear? So here you will be having over this face we have sigma 1. Sigma 1 is 54.2. So I will represent 54.2 over this face. It will be like positive value, so it will be like this. Clear? And over this face we have sigma 2. This is sigma 1 and sigma 2 is minus, so it will be compressive, so sigma 2. And maximum in plane shear, for maximum in plane shear, this normal stress over this surface will be average stress. This is sigma average and this angle will be 29.5 degree and you will be having a in plane shear stress over this surface will be like this. It will be like this. This is tau max in plane. You can just pick the value. Sigma average is 25 megapascal, sigma 1 is 54.2, sigma 2 is 4.15 megapascal compressive. And that was all about this problem 9-16, in which we have calculated the principal stresses sigma 1 and sigma 2 and their orientation and specify the orientation on element. And in second part we have find out the maximum in plane shear stress and average stress and their orientation and specify on the element. And by combining these two you can also specify the state of stress on the element. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest video. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. Problem 9-17. This is taken from chapter number 9, that is stress transformation, and book name is Mechanics of Material by R.C. Hibbeler. So statement is determine the equivalent state of stress on the element at same point which represent the principal stress, and in B part maximum in plane shear stress and associated average normal stress. Also, for each case, determine the corresponding orientation of the element with respect to the element shown. Sketch the result on the element. So you can see this is a state of stress. This is x-axis. This is your y-axis. Clear? So you can see this is your x-axis and this is your y-axis, and you have taken this as sigma x, which is 125 megapascal, sigma y is compressive, so it will be minus 75, and tau of xy, this is x plane and y is in downward direction, so tau of xy is minus 50 megapascal. So you have to find the principal stresses, which is sigma 1 and sigma 2, and in B part maximum in plane shear stress and average normal stress, and then we will also draw the orientation of these elements. So let's start with the solution. So for principal stresses, we know that principal stresses is equal to sigma 1 comma 2, that is equal to sigma average plus minus sigma x minus sigma y divided by 2 whole square plus tau of xy square, and sigma average is actually equal to sigma x plus sigma y divided by 2. So put the value, we have sigma 1 comma 2 is equal to sigma average is equal to sigma x plus sigma y divided by 2, so 125 plus minus 75 divided by 2 plus minus sigma x, which is 125, minus sigma y is minus 75 divided by 2 whole square plus tau of xy, which is minus 50 square. So when you add these two terms, you will get sigma 1, which is 137 megapascal, and when you subtract these two terms, so you will get sigma 2, which is equal to minus 86.8 megapascal. So these are the principal stresses. Now we'll specify the orientation. Clear? So for orientation, we know that are the angle through which this principal stresses act. So this angle is equal to tangent of 2 theta p is equal to tau of xy divided by sigma x minus sigma y divided by 2. Clear? So put the value, minus 50 divided by sigma x is 125 minus 75 divided by 2. So you will get it minus 0.5. So tangent of 2 theta p is equal to minus 0.5. So what we will do is that we will get this 2 theta p will be equal to minus 26.75 degree, or theta p will be equal to minus 13.28 degree. Now this is the angle. Clear? So if your x-axis is like this, initially x and y was this. Clear? So now due to this angle, which is minus 13.2, this is theta p, which is equal to minus 13.28 degree, and your y dash will be this one. Clear? And if you draw the element like this, so you must know on this face which one stress is acting, either this one or this one. So for that we will use stress transformation equation, and we will put the theta in that. So we know that stress transformation equation is equal to sigma x dash is equal to sigma x plus sigma y divided by 2 plus sigma x minus sigma y divided by 2 into cos of 2 theta. So this is cos of 2 theta plus tau of xy sine of 2 theta. So put the value, you will get sigma x dash is equal to 125 minus 75 divided by 2 plus 125 minus 75 divided by 2 into cos of minus 13.28 degree plus tau of xy, and tau of xy is minus 50. So 50 into sine of minus 13.28 degree. So when you calculate it, you will get sigma x dash is equal to 137 megapascal. So it means that over this phase we have this 130 sigma 1 that is acting. So we will represent it over this phase. So over this phase we have, this is sigma 1 which is positive, so it will be tensile 1. Clear? This is sigma 1, and sigma 2 is compressive, which will be like this one. This will be sigma 2. So we have solved our part 1. Now we'll move towards second part, and in second part we have been asked to find out the maximum in plane shear stress and average normal stress associated with it. So we know that maximum in plane shear stress can be obtained by this formula, which is equal to sigma x plus minus sigma x minus sigma y divided by 2 whole square plus tau of xy whole square under the root. Okay. Now proceeding further, we can put the values over here. So if you put sigma x is 125 minus sigma y is minus 75 divided by 2 whole square plus tau of xy, which is minus 50 whole square under the root, and this will give you 112 megapascal. And average normal stress associated can be obtained by using this formula, sigma x plus sigma y divided by 2. So 125 minus 75 divided by 2 will give us the average normal stress, which is equal to 25 megapascal. Now we'll find the orientation of this plane of maximum in plane shearing stress. So orientation of in plane maximum shear stress can be obtained by using this formula, tangent of 2 theta s is equal to minus sigma x minus sigma y divided by 2 divided by tau xy. So put the value minus 125 minus 75 divided by 2 divided by tau of xy, which is minus 50, and that will give you 2. So we will get tangent inverse of this 2 will be equal to 2 theta s, and this theta s will be equal to this 2 theta s will be equal to 63.4 degree, or theta s will be equal to 31.7 degree. Okay, now we will represent them on, specify it on elements. So this is your x, this was your y. Clear? Now the angle is positive, so it means counterclockwise, so this will be 31.7, which is equal to theta s. and your y dash will be like this. And if you specify the element, so it will be like this. Clear? Here you can see that you will be having shear force in this direction, and your normal force, which are average force, which will be in this direction. This will be your sigma average. This will be your sigma average. This will be like this. Now if you want to represent both state of stress in one diagram, so what we will do is that let this was your initial x-axis, and if you move 13.28 degree in this clockwise direction, so you can see this is clockwise, so this will be again, this will be clockwise, and draw the element one face perpendicular to this and other one is like this. So your principal stress is sigma 1 will be in this direction. Clear? This is your sigma 1, and your sigma 2 will be this sigma 2, and your in plane shear stress will be acting, your in plane shear stress will be acting on this face. Clear? This is maximum in plane shear stress, and your normal force acting to that will be this average stress, which will make an angle of 31.7 degree. Clear? This is, so sigma 1 was 137 megapascal, sigma 2 was minus 86.8 megapascal, maximum in plane shear stress is 112 megapascal, and average normal stress is 25 megapascal. So this is the combined representation or orientation of these stresses on the element. And that was all about this problem 9-17. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching. Welcome back. In this video, we are going to solve problem 9-18 that is taken from chapter number 9, Stress Transformation, and book name is Mechanics of Material by R.C. Hibbeler. So statement is a point on a thin plate is subjected to two successive state of stress as shown. Determine the resultant state of stress represented on the element oriented as shown on the right side. So you can see these are the two successive state of stress. Clear? And we have to show that the sum of these two will be equal to this, and we will find this sigma x, sigma y, and tau of xy. So let's start with the solution. So we will name this case as A and this case as B. So you can see this is the case A that is shown over here. So if you want to convert it into this form, so this angle is 45. Let me show you. This angle is 45. So this angle will be also 45 because this is 90 and this remaining is 45. So this total sum is 90. So 45, 90 minus 45 will be also 45. So here we can say that let this is your axis which is represented as x, and this is your axis which is represented as y. Clear? And for the new axis, transform axis, this will be x dash, and your this axis will be y dash. So we know that this axis, this theta is equal to clockwise, that is minus 45 degree. So theta is equal to minus 45 degree. Clear? You can see that sigma x, which is in this direction, is 85 megapascal, and sigma y in this direction is also 85. So sigma x is 85 megapascal, sigma y is also 85 megapascal, and you can see there is no shear stress, so tau of xy is equal to 0. So by using stress transformation equation, our new stress in x dash direction will be equal to sigma x plus sigma y divided by 2 plus sigma x plus sigma y divided by 2. This is minus, not plus. So you have to memorize these formulas, into cos of 2 theta plus tau of xy sine of 2 theta. So I will put the value 85 plus 85 divided by 2 plus 85 minus 85 divided by 2, and cos of theta is 45, so cos of 2 theta is minus 90 degree, plus 0 into sine of minus 90 degree. That will give you sigma x dash. So sigma x dash, when you calculate, will be 85 megapascal. So it means that in this x dash direction, your sigma x dash will be 85. So this will be your sigma x dash. Okay, now we will find sigma y. So for sigma y dash, we know that sigma y dash is equal to sigma x plus sigma y divided by 2 plus sigma x minus sigma y divided by 2 into cos of 2 theta minus tau of xy sine of 2 theta. So again put the value 85 plus 85 divided by 2 plus 85 minus 85 divided by 2 into cos of minus 90 degree minus 0 into sine of minus 90 degree. That will give you sigma y dash, and when you calculate it, you will get sigma y dash will be also equal to 85 megapascal. So our sigma y dash, which we will represent on this element, will be this one, sigma y dash. It will be like this. Clear? Now we'll find tau of xy. So for transform, so tau of x dash, y dash, and all these are for case A. So I will put A over here. So tau of x dash, y dash for A is equal to minus sigma x minus sigma y divided by 2 into sine of 2 theta plus tau of xy cos of 2 theta. So put the value minus 85 divided by 2 into sine of minus 90 degree plus 0 into cos of minus 90 degree will give you tau of x dash, y dash for case A. So when you calculate it, you will get this will comes out to be 0. It means that there is no shear stress in this condition. So we have only sigma x dash and sigma y dash, which we have calculated. Both comes out to be 85 megapascal. Now we will move toward case B, and for case B I have already shown it over here. So you can see that this will be your the line that is perpendicular to this face will be equal to x, and this will be equal to y. And you can see that this angle is 60 degree. So this angle is 60 degree. Clear? So if you rotate it as a 60 degree, so this will be your x-axis, and we are converted into x dash, and this will be your y dash. So we will convert theta here is again equal to minus 60 degree, that is clockwise. So here theta is equal to minus 60 degree. You can see that sigma x and sigma y both are equal to 0, and only we have tau of xy is 60 megapascal. So this is tau of xy, 60 megapascal. So we will convert, when you rotate it minus 60 degree or 60 degree clockwise, so your transformation sigma x dash for b, you will use the same formula. This is the formula. So put the value, sigma x is 0 plus 0 divided by 2 plus 0 minus 0 divided by 2 into cos of 2 theta. So cos of minus 120 theta is minus 16 plus tau of xy. So tau of xy is 60 into sine of 2 theta. So sine of 2 theta is minus 120 degree. So when you solve this, you will get sigma x dash for case B comes out to be minus 51.96 megapascal. Similarly, you can find sigma y dash for B case will be equal to, you will use this formula. Note down this formula. Clear? This is the formula. Note down this formula. So 0 plus 0 divided by 2 plus 0 minus 0 divided by 2 into cos of minus 120 degree minus 60 into sine of minus 120 degree. And again, when you calculate it, you will get sigma y dash for case B comes out to be, this will be plus 51.96 megapascal. And tau of x dash y dash for this case B will be equal to, you will use this formula. So it will be minus 0 divided by 2 into sine of minus 120 degree plus tau of xy, which is 60 into cos of minus 120 degree. And when you calculate it, you will get this will be equal to minus 30 megapascal. Now for this, if I draw the state of stress, like this is the state of stress, when you convert it in along x dash, you have minus 51.60. so minus 51.60 means that this is compressive. So this is sigma x dash for B. Clear? And sigma y is 51.6. So it will be tensile. This is sigma y dash for this case B. And tau of x dash y dash is minus 30. So it will be like this. Okay. Now you have both the cases. This is tau of x dash y dash for B case. Now you can see that we have been given that this plus this is equal to this. So what we will do is that we will take its x dash component, y dash component, x dash component, y dash component, and again for this x dash and y dash component, and we will add it. So this sigma x will be equal to this sigma x will be equal to sigma x dash for A plus sigma x dash for B. Similarly, this sigma y dash, sigma y will be equal to sigma y dash for A plus sigma y dash for B, and the tau of xy for this component will be equal to tau of x dash y dash for A plus tau of x dash y dash for B. So let me write it. You can see that this sigma x will be equal to sigma x dash for case A plus sigma x dash for case B. So for A it is equal to 85 megapascal, and for B it is minus 51. So 85 minus 51.96 will be equal to 33 megapascal. Similarly, sigma y will be equal to sigma y dash for case A plus sigma y dash for case B. So for case A it is equal to 85, and for B it is 51. So 85 plus 51.96 will give you 137 megapascal. And the last one is tau of x dash y dash, tau of xy. Tau of xy will be equal to tau of x dash y dash for case A plus tau of x dash y dash for case B. So for case A it was 0, and for case B it was minus 30. This is for case A, and for this is case B. So it is equal to minus 30 megapascal. And this is how we have calculated the answer of our this question. So in last you can say that this sigma x is equal to 33 megapascal. Clear, sigma y is 137 megapascal, and this is minus 30 megapascal. And that is all about this problem 9-18. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it, and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching.